Welcome to Lecture 9 of How to Read and Do Proofs. Welcome back, everybody. Today we're going to learn a new proof technique. And that's a good thing because in spite of all of the proof techniques you've learned so far, you still might not be able to complete a proof for one reason or another. Let's take a look at an example. Here's the definition of an even integer. An integer n is even if and only if there is an integer k such that n is equal to 2k. What we want to prove is that if n is an integer and n squared is even, then n is even. Hopefully you have identified the hypothesis A and the conclusion B and have decided on a proof technique to get started with. In particular, you should look for keywords such as there is and for all. Not seeing any, what proof technique should you use to get started with?
The forward-backward method.
The forward-backward method, for which we're going to ask the key question, how can I show that an integer is even? Using the definition, one way to show that an integer is even is to show that there is an integer k such that n is equal to 2k. Can somebody tell me what proof technique you would use now?
The construction method?
Yes, the construction method, because you see the keywords there is in the backward process. So you know that you have to construct an integer k for which n is equal to 2k. And in fact, when I see the keywords there is, and I recognize that I have to use the construction method, I typically turn to the forward process to try and construct that object. So here what we're going to do is turn to the forward process and work forward from the fact that n squared is even. Because n squared is even, again, by definition, there is an integer, let's call it p, not to confuse with k. There is an integer p such that n squared is equal to 2p. The goal is to see if we can use the integer p to construct the integer k. Now we know that n squared is equal to 2p, but we're interested in n, so it seems reasonable to take the square root of both sides of this equality. And if we do that, we get n is equal to the square root of 2p. The question, however, is how do you rewrite the square root of 2p to equal 2 times k? And that turns out to be not so easy to do. So it would appear that the forward-backward method has failed here. With the technique that you're about to learn today, what we're going to do is be able to prove this proposition very easily. And so that technique is called the contradiction method. When you want to show that A implies B is true, you can assume that A is true. Your job is to show that B is true. The contradiction method comes about by asking yourself a very simple question. Why can't B be false? I mean, after all, if B is supposed to be true, there must be some reason why B can't be false. And that's the goal of the contradiction method. The goal of the contradiction method is to find the reason that B cannot be false. Let me describe the contradiction method in another way. Let's recall the truth table for A implies B. Here's the truth table. And if you recall, we agreed that A implies B is true in all of these cases except when A is true and B is false. With the contradiction method, what we're going to try to do is rule out case 2. If I can rule out case 2, doesn't that mean that A implies B has to be true? So the question is, how do we go about ruling out case 2? And here's how we do that. We actually assume that case 2 happens. That is, we assume that A is true and B is false. From here on, I'm going to write the statement that B is false as not B. So we assume A is true and B is false, and then somehow we need to see why this cannot happen. What does it mean to see that this cannot happen? Well, suppose that as a result of assuming A is true and B is false, suppose I can convince you that 1 is equal to 0. Wouldn't that be a reason why it cannot be that A is true and B is false at the same time? Because if A were true and B were false at the same time, that would mean 1 equals 0, and we know that 1 can't equal 0. So to summarize, with the contradiction method, you assume that A is true and B is not true. That is, you assume A and not B, and you try to reach a contradiction to something that you absolutely know is true. Now, this should raise several questions. For example, what contradiction should you be looking for? And unfortunately, I can't answer that question because each problem gives rise to its own unique contradiction. And this is the art of doing a proof by contradiction. You do not know what the contradiction is going to be beforehand. Let me give you some examples of contradictions. So obviously 1 equals 0 is a contradiction. Here's another contradiction. The sum of the degrees of the angles of a triangle in the plane is more than 180 degrees. That's a contradiction. Here's another contradiction. Some statement C is both true and not true at the same time. That can't happen. So there are many contradictions out there, and your goal with the contradiction method is to find a contradiction. So here's another good question. How exactly are you going to use A and not B to reach a contradiction? And that I can tell you. You're going to simply work forward from A and not B. That's all there is to it. Work forward from A and not B to get to a contradiction. That leads to our last question. When and why should you use the contradiction method? And the contradiction method is a keyword technique. And in particular, what you should do is use the contradiction method when the conclusion of your proposition contains the keywords no or not. In fact, you should think about using the contradiction method whenever you encounter the keywords no or not in the backward process. So let's take a look at comparing the contradiction method and the forward-backward methods. So with the forward-backward method, can somebody tell me what do you assume is true?
A.
A is correct. And what do you try to show is true?
B.
B, good. And how do you do that? You work forward from A and backward from B. Everybody okay? All right. With the contradiction method, what should you assume is true?
You should assume that A is true.
And?
B is not true.
A and not B. Assume A is true and B is not true. And what should you try to conclude?
A contradiction.
A contradiction. And how exactly are you going to do this? By working forward from A and not B. Any questions on this contradiction method?
And there is no backward method?
Well, that raises the next question. Good observation. By looking at this diagram, can you see a potential advantage of contradiction over forward-backward?
There are 2 places to work forward from?
There are 2 statements to work forward from as opposed to 1 in the forward-backward method. Exactly. The advantage of the contradiction method is that you can work forward from 2 statements, namely A and not B. That's the advantage. However, there's a potential disadvantage of the contradiction method. Eleanor, what was it that you observed?
That there was no backward process.
Yes, how can you work backward from a contradiction that you don't even know what it is? There is no backward process. And this can be a tremendous disadvantage. So in essence, with the contradiction method, you work forward from A and not B, but you're working forward in a blind way trying to find this contradiction. All right, let's see an example of using the contradiction method. And let's go back to the proposition we wanted to prove earlier in this lecture. But this time I'm going to use the definition of an odd integer. So an integer n is odd if and only if there is an integer k such that n is equal to 2k plus 1. So 7 is odd because 7 can be written as 2 times 3 plus 1. And again, we want to prove that if n is an integer and n squared is even, then n is even. Now, when we looked at this proposition before, what proof technique did we use to get started with?
The forward-backward method?
The forward-backward method, because we saw no keywords, correct? All right. Look at the conclusion B here, n is even. And I hope you'll agree with me that we can rewrite this statement, n is even, in a slightly different way. Let's write it this way. N is not odd. Do you agree that if n is even, then n is not odd, and if n is not odd, n is even? Now, the advantage of writing B in this form is that you can see a keyword here. What keyword?
Not.
Right. And when you see the keyword not, that should trigger or make you think about using the contradiction method. So, as a result, let's remember how the contradiction method works. When you decide to use contradiction to show that A implies B is true, what should you assume?
A
is true.
Not B?
A and not B. So what is A here?
N is an integer and n squared is even.
N is an integer and n squared is even. And now look at B here. What is the negation of B? What is not B?
N is odd?
N is odd. That's using one of the rules we learned in negating a statement. So we now have to do what? We can assume A is true and B is not true. And what do we have to do next?
Work forward?
To do what?
Find a contradiction?
Work forward to reach a contradiction. That's exactly what we're going to do now, and you're going to see that that's actually very easy to do. So let's work forward from the fact that N is odd. And you can see that we have a definition up here. So because N is odd, there is an integer k for which N is equal to 2k plus 1. This is working forward by definition. And now notice that we're interested in N squared. So let's square both sides of this right here and write as a new forward statement, N squared is equal to 2k plus 1, the quantity squared. And now let's do a little bit of algebra. Let's expand this and write it as 4k squared plus 4k plus 1. And this I'm going to rewrite as follows. 2 times the quantity 2k squared plus 2k plus 1. So N squared is equal to 2 times some integer plus 1. What does that mean about N squared? Is it odd or even?
It's odd.
It's odd. N squared is equal to 2 times some integer plus 1. N squared is odd. And now you have a contradiction, because look at A3. A3 says that N squared is odd, but A says that N squared is even. How can N squared be both odd and even at the same time? That's impossible. That's a contradiction. And it's that contradiction that completes the proof. Let's do another example. Let me ask you to recall the definition of a rational number. A real number R is rational if and only if there are integers p and q with q not equal to 0 such that R can be written as p over q. In other words, R is a fraction. All right, here's what we want to prove now. If R is a real number for which R squared equals 2, then R is irrational. Now, before we prove this, what I'd like to ask you to do is take a moment to read this proposition and try to understand what it is saying in words. This proposition is telling us that the square root of 2 is not rational, cannot be written as a fraction. And this is something that's important. You know, right now we're learning all these proof techniques and we're thinking about them and so forth. But eventually, when you learn these proof techniques, you don't have to think about them so much and you can focus on the mathematics. We state propositions like this and prove them not to harass students, but because they tell us something very interesting or very useful in terms of solving problems and knowing more about the world around us. Let's start the proof. So of course you've identified the hypothesis A and the conclusion B. And what do you do next?
Identify a proof method?
Choose a proof technique based on keywords. And in particular, do you see any keywords?
Not rational, so not would be the key word.
Exactly. Irrational means not rational, and therefore what proof technique might you think about using here?
Contradiction.
The contradiction method, exactly. Recognizing that irrational means not rational, you should therefore proceed by the contradiction method, and therefore, what should you assume is true?
The statement A and the statement not B.
All right, A and not B. A is, R is a real number for which R squared equals 2. Can somebody tell me what is not B?
R is rational.
R is rational. And this is what we're going to assume. And what do we have to do with this now?
Work forwards.
Work forward to do what?
To find the contradiction.
Work forward to get a contradiction. Exactly. So let's work forward from the fact that R is rational by definition. There are integers p and q with q not equal to 0 such that R is equal to p over q. That's the definition of a rational number. Now, in order to reach a contradiction, you would start working forward from here in the blind, not knowing what the contradiction is going to be. However, because I have read this proof before, I know what the contradiction is going to be. And to help get that contradiction, we need a very interesting observation. Look at A2. It says that there are integers p and q with q not equal to 0 for which R can be written as p over q. It can be further assumed that p and q have no common divisor other than 1. That is, there's no integer that divides both p and q other than 1. Let's take a look and see what this means. Suppose we're thinking about p equals 6 and q equals 18. So r is equal to 6 over 18. 6 and 18 have a common divisor. What common divisor?
6.
6, 3, 2, right? So let's rewrite 6 over 18 as 1/3. Now, 1 and 3 have no common divisor other than 1. So we can assume that P and Q have no common divisors other than 1, because if they did have a common divisor, we could simply divide that out of both the numerator and the denominator. I'm going to show you the contradiction that P and Q can both be divided by 2. In other words, that P and Q are both even. And that will be a contradiction. How can P and Q have no common divisor and at the same time have 2 as a common divisor? That can't happen. Here's what we're going to do. Work forward from A and A2 to show that both P and Q are even. And what I'm going to do here is put up some statements, and maybe you can help me with the reasons. So, for example, I claim that r squared is equal to p squared over q squared. What's the reason for that? How did I get that?
You squared both sides.
Of what?
Statement A2.
That's correct. I simply squared both sides of A2. If r is equal to p over q, then certainly r squared is equal to p squared over q squared. Okay? Here's another statement. 2 is equal to p squared over q squared. How did I get that?
From the statement A.
From the statement A. R squared is 2, and r squared equals p squared over q squared, so put in 2 for r squared right there, and you get 2 is equal to p squared over q squared. Okay, now for this next one, you don't need a PhD. How did I write 2q squared equals p squared?
Just multiply a5 by q squared.
Exactly. That's why I told you, you don't need a PhD for this one, right? Multiply a5 by q squared. Okay. So now look at what this is saying. P squared can be written as 2 times some integer. What does that mean about p squared in terms of being odd or even?
It's even.
P squared is even by definition. Now remember previous knowledge. We proved earlier today that if n is an integer and n squared is even, then n is even. So if p is an integer and p squared is even, then what do you know about p?
P is even.
P is even. That's previous knowledge from Proposition 11. And by definition, what does that mean? There is an integer k such that p is equal to 2k. All right, now let me ask you to look back at A6. If you look back at A6, it says that 2q squared equals p squared. But we know that p is equal to 2k from A9, so let's put 2k in here for p, and we get 2k the quantity squared, which is otherwise known as 4k squared. And let's call that statement A10. So that's substituting p equals 2k. Now I'm going to write q squared equals 2k squared. How did I go from A10 to A11?
Divided by 2.
Divide both sides by 2. And look at what this is saying. Q squared can be written as 2 times some integer. What does that mean about q squared in terms of being odd or even?
It's even.
Q squared is even. Q squared is even because q squared can be written as 2 times some integer. So now we know that q is an integer and q squared is even. So from our previous proposition, what do we know about q?
Q is even.
Q is even. That's from Proposition 11. So now look carefully at A8 and A13. A8 says P is even. A13 says Q is even. That means they both can be divided by 2. But that's a contradiction. We said you can assume that P and Q have no common divisor. But in fact, they do have a common divisor, 2. And that contradiction completes the proof. So what we'd like to do now is we'd like to practice reading proofs. So to read this next proof, we need a definition of a bounded set. So we have a set of real numbers. Let's draw a picture here. Here's the real line. Let's put a set of real numbers there. A set of real numbers is bounded if and only if there is a real number epsilon greater than 0, such that for every element x in S, the absolute value of x is less than epsilon. So let's look at the picture and understand why is this set bounded. This set is bounded because there is an epsilon greater than 0 with the property that all the elements in the set have absolute value less than epsilon. That is, all the elements in the set have a value between minus epsilon and plus epsilon. In words, a set is bounded if it's not too big. So what we want to prove now is the following proposition. If S is a subset of T and S is not bounded, then T is not bounded. Now I'm going to put up a proof and ask you to read it. Before I do that, I hope everybody has identified the hypothesis A, the conclusion B, and even thought about what proof technique you would use to begin this proof. In any case, here's a condensed proof. Please take a few minutes to read this. Okay, our goal is to explain each of these sentences in the context of proof techniques. In other words, this author is using the proof techniques that you've learned, but has not mentioned those proof techniques explicitly by name. So to get started, of course, the first step is to identify the hypothesis A and the conclusion B. Now we want to interpret what the author has written in the first sentence. Assume to the contrary that T is bounded. Can somebody tell me what proof technique the author is using in this sentence and why?
Contradiction.
You're right. This is a proof by contradiction, as indicated by the words to the contrary. Why did the author choose the contradiction method?
Because the keyword not is in the statement B.
Because the keyword not is in the conclusion. Exactly. So now we have to remember how the contradiction method works. In other words, what should you assume is true?
The forward statement.
So what should you assume is true?
That S is a subset of T and S is not bounded.
You should assume the statement A, S is a subset of T and S is not bounded. And what else should you assume?
That the statement B is not true.
That the statement B is not true. What does it mean to say it is not true that T is not bounded?
T is bounded.
T is bounded, exactly. And that's exactly what the author has written in S1. Assume to the contrary that T is bounded. That is not B. What now does the author have to do?
Work forwards from these two statements to a contradiction.
Exactly. Work forward from A and not B, in other words, A and A1, to reach a contradiction. When you are reading a condensed proof and you discover that it is a proof by contradiction, I would urge you to go back to the proof and find the contradiction. So let's do that here. Let's back up. I want you to take a moment to look at this proof here and see if you can identify the contradiction. Take a moment to read it. See if you can find the contradiction. Don't read for details. Just try to get the big picture and see if you can identify a contradiction. What contradiction did you find?
In the statement S5, it says that S is bounded, but in the proposition, it says that S is not bounded.
In the hypothesis, it said S is not bounded. How can S be bounded and not bounded at the same time? That's the contradiction. And let me point out that this is an interesting difference between doing a proof by contradiction and reading a proof by contradiction. When you do a proof by contradiction, you get to assume that A is true and B is not true, but you have to work forward in the blind because you don't know what the contradiction is going to be. However, when you read a proof by contradiction, you can read ahead in the proof and find the contradiction. And that's a useful thing to do because you should always keep in mind what the contradiction is as you are reading the proof. Okay, let's return to reading the proof. The contradiction is going to be that S is bounded. That means the author has to show that S is bounded. So here's where we are. You can assume A is true and B is not true, and this author is going to work forward from here to show that S is bounded. All right, let's see what the author writes next. Hence, there is a real number epsilon prime greater than 0 such that for every element x in T, absolute value of x is less than epsilon prime. Where did that statement come from?
Through definition?
That is exactly the definition of the set T being bounded. A set T of real numbers is bounded if and only if there is a real number, in this case the author calls it epsilon prime instead of epsilon, greater than 0 such that for every element x in T, absolute value of x is less than epsilon prime. This is the definition of a bounded set, in particular T being bounded. So the author has worked forward from A1 by definition to write this. Now the author says, let x prime be an element of S. In order to understand where this statement came from, you're going to have to work backward from B1. So can somebody ask a key question here? How can I show that?
S is bounded.
S is bounded. You're using symbols.
A set is bounded.
A set is bounded. That's a good key question. How can you show a set is bounded? By definition, you have to show that there is a real number epsilon greater than 0 such that for every element x in S, absolute value of x is less than epsilon. So this becomes the new backward statement that the author has to show. So we're going to work forward from A2 and backward from B2. Here's where we are. We're still trying to interpret what the author has written when the author says, now let x prime be an S. And again, in order to determine what is going on here, we have to do some work ourselves. So let's look at the statement B2, and can somebody tell me what proof technique would you use to show that B2 is true?
The construction method.
The construction method. The author must construct a real number epsilon greater than 0 such that for every element x in S, absolute value of x is less than epsilon. And without telling you, the author has constructed the value of epsilon equal to this epsilon prime that we know exists from A3. Now you have to remember how the construction method works. You go and construct the object. Is that the end of the proof? No. What do you have to do? After you construct the object, you have to show it's the right one. Meaning what?
Something happens.
The certain property and the something that happens. So for the construction method, you must show that the certain property happens, and that certain property is being positive. But we know epsilon prime is positive because we have it right up here. And we have to show that the something happens. So it remains to show that for every element x in S, the absolute value of x is less than epsilon prime. And notice that all of this is going on in the author's head without telling you. All right, so here we are. The author has constructed epsilon equal to epsilon prime, which we know is positive from A2. It remains to show that for every element x in S, absolute value of x is less than epsilon prime. We now are still trying to interpret the sentence S3. Now let x prime be an S. To understand this sentence, look at B3. Can somebody tell me what proof technique would you use to show that B3 is true?
The choose method?
The choose method. So now you have to recall how the choose method works. How does the choose method work? What should I choose?
An element in set S?
Choose an element in the set S. And notice that that is exactly what the author has said in S3. Let x prime be an element of S. the author is using the choose method. And what does the author have to show?
That the something happens?
That the something happens, namely the absolute value of x prime is less than epsilon prime. And now I hope at last you can understand the statement, let x prime be an S. What the author has done is used the choose method after realizing that first you have to do the construction method, and as part of the construction method you have to show that for every element x in S, absolute value of x is less than epsilon prime, and this, keywords for all in the backward process, indicate that the choose method should be used. Look at how much work went into this one sentence. And the only way you'll understand this is if you start to do the proof yourself, or at least understand what proof techniques are needed. So here we are, almost finished, not quite. Let's look at what the author writes next. Because S is a subset of T, it follows that x prime is in T. What proof technique is the author using when the author says because S is a subset of T?
They're working forwards from A.
They're working forward from A, exactly. So let's work forward from the fact that S is a subset of T. What does that mean by definition?
That all the numbers in the subset are in the set?
That's correct. Every element in S is also in T. For every element x in S, x is in T. And in terms of proof techniques, I hope you recognize a key word here. What key word?
For all?
For all in the forward process. What proof technique should the author now use?
Specialization method.
Specialization. And that means you need to recall how the specialization method works. In particular, you need to find one object with the certain property, one element x in the set S. Do you see a particular element x in the set S?
X prime?
X prime. We chose an element x prime in S. There is a particular object with a certain property. So we're going to specialize this A5 to one particular value of x. Which particular value of x? X prime, an object with a certain property. And what's the result of specialization?
That x is an element of T, or x prime?
X prime is an element of T, right? You apply the something that happens to this particular object that you are specializing to. So the result of specialization is a new forward statement, x prime is in T, and that's exactly what the author has written here. So here's where we are. We're still trying to get to B4. Let's see what the author writes next. But then the absolute value of x prime is less than epsilon prime, and so S is bounded, which is a contradiction. The question that we need to figure out is, how does the author reach the conclusion that the absolute value of x prime is less than epsilon prime? And the answer turns out to be that the author is using one of our proof techniques, again, but which one? And the answer comes from looking at A2 and noticing a for all statement in the forward process. What proof technique do you use when you know that for every object with a certain property, something happens?
Specialization.
Specialization. So we need to specialize this statement to one particular element in T. Any suggestions on what particular element of T we can specialize to?
X prime?
Again, x prime in T. How do you know x prime is in T? Well, that's exactly what A6 is all about. X prime is in T, so it is an object with a certain property. And what is the result of specialization?
That the something happens?
That the something happens. The absolute value of x prime is less than epsilon prime. And that's exactly what the author has written right there. But then, absolute value of x prime is less than epsilon prime. The author has applied specialization to reach that conclusion. But if you notice, A7 is precisely before the last statement in the backward process, and this completes the proof. Notice how many different proof techniques the author has actually used without telling us. The construction method, the choose method, the specialization method, the forward-backward method, all of these methods have been used without mentioning it to us. The only way you can learn to understand these kind of condensed proofs is by learning to identify what techniques the author is using and how they're being used and filling in details. Okay, there are some other very nice uses for the contradiction method. In fact, whenever you want to prove that any statement is true, you can always try to prove it by contradiction. How? Assume that the statement is not true and show that that leads to a contradiction. In particular, let's take an example. Suppose you want to show that there is an object with a certain property such that something happens. What proof technique would you use to show that there is an object with a certain property such that something happens?
The constructive method.
The construction method. So you already know about that. However, if you want to show that B is true, you can do that with contradiction. And here's how that would work. You would assume that B is not true. What is the negation of the statement B?
For every object with a certain property, the something does not happen.
Exactly. So you could assume that B is not true. That is, that for every object with a certain property, the something does not happen, and then try to reach a contradiction. See how powerful contradiction is? It gives you a whole new approach to showing that any statement is true. Just assume that the statement is not true and reach a contradiction. However, I would like to point out that there's a big difference between using the construction method to prove that there is an object with a certain property such that something happens, and using the contradiction method. In particular, when you use the construction method to show that B is true, what you will have done is actually gone out and constructed the object, right? That's what the construction method is all about. You will actually have constructed the object. However, when you use the contradiction method to prove that B is true, you will not have actually constructed the object. What you will have done is shown that this statement must be true, because if it were not true, that would lead to a contradiction. So, with the contradiction method, you will know that there is an object with a certain property such that something happens, but you will not have constructed it. Everybody see the difference between using the construction method and using the contradiction method? In both cases, you'll know that this statement B is true. But with the construction method, you'll have produced the object and shown it's the right one. With the contradiction method, you'll know that this object exists, but you won't have produced it. In fact, an area of active research is to take proofs that have been done in the past by the contradiction method and try and do them constructively, try and actually produce the object. Let me summarize the contradiction method. With the contradiction method, you rule out the one case when A implies B is false. And how do you do that? You assume it happens. You assume that A is true and B is not true, and you use that information to work forward and reach some kind of a contradiction. When should you use the contradiction method? When you see the keywords no or not anywhere in the backward process. That should be a signal for you to think about using contradiction. That completes this lecture.